Assume that we have these two matrices, a matrix A 5, 2, 2, 1, and a matrix B 1, minus 2, minus 2, 5. These are 2 by 2 matrices. And we want to multiply these two matrices. So let's see A, B. So 5, 2, 2, 1 multiplied by 1 minus 2 minus 2, 5. So I know that I need to multiply first row, first column of the second matrix to obtain the element that is in the first row, first column of the matrix result. So that will be equal to 5 times 1 is 5 minus 2 times 2 minus 4. So it will be 5 minus 4. That will be the first element in the first row. Now for getting the second element of the first row will be the first row of the first matrix multiplied by the second column of the second matrix. It will be 5 times minus 2 minus 10 plus 2 times 5, so plus 10. So it will be minus 10 plus 10. Here, the element in the second row, first column of the result will be the product of the second row of the first matrix multiplied by the first column of the second matrix. Will be 2 times 1 plus 1 times minus 2. So it will be 2 minus 2. And finally, the last element will be 2 times minus 2, this will be minus 4, plus 1 times 5. It will be minus 4 plus 5. Simplifying, we are going to obtain 5 minus 4, this is 1. This is minus 10 plus 10 is 0. 2 minus 2 is 0. And then minus 4 plus 5 is 1. We have obtained the identity, the 2 by 2 identity. So multiplying these two matrices produces the identity. We say in this case that A is the inverse of B, or that B is the inverse of A. So these two matrices behave as two numbers that are the inverse of the other. For example, when we multiply 5 times 1 over 5, the answer is 1. Sometimes we multiply two numbers and we get the identity of the multiplication, that is number 1. So these two matrices behave as these two numbers. So we notice that the multiplication in matrices have this property that have the number. Sometimes a number have an inverse, and the inverse is another number that multiply, you get number 1. Almost every real number have an inverse for the multiplication. The only number that doesn't have an inverse for the multiplications is number 0. There is no number that multiply by 0 you get 1. Here in matrices you are going to notice that will be not only one matrix, many matrices that doesn't have an inverse. So, but let's first define the concept of inverse of a matrix. Let A and B be matrices of size n by n, such as AB equal BA equal the identity of size n. Then we say that A is an invertible matrix and that B is the inverse of A. And we write in this way, A, like the power, like to the power -1 equal B. So we put the -1 as the power of the matrix, and we write the inverse of A is equal B. We also say that the inverse of B is A. And for example, one example will be the one that we have already shown you, that we have the two matrices and we already multiplied the two matrices, and we found that when we do that, the product is the identity. So for that, we can say that B is the inverse of A, or A is the inverse of B. Another example could be these two matrices. Let's see this C, 1, 5, minus 1, minus 0.5, 0.5. And this matrix D equal 2, 4, 2, 6. To see if they are actually one, if the inverse of the other, we multiply the two matrices CD let's say this multiplied by this, and then you multiply the first row multiplied by the first column of the second matrix, and that will be equal 1.5 times 2 is 3, and this minus 1 times 2 is minus 2, so it will be 3 minus 2, the first element of the product. And the second element of the first row of the product will be 1.5 times 4, this is 6, minus 1 times 6 will be negative 6, so 6 minus 6. Here will be minus 0.5 times 2 equal negative 1, and 0.5 times 2 is plus 1, so it will be negative 1 plus 1. And finally, the last entry of this row will be the second row of the first matrix multiplied by the second column of the second matrix. Minus 0.5 times 4 is negative 2, 0.5 times 6 is positive 3, so it will be negative 2 plus 3. So I close the bracket, and then the answer will be 3 minus 2 is 1, 6 minus 6 is 0, here minus 1 plus 1 is 0, minus 2 plus 3 is 1. So checking that one matrix is the inverse of the other is just multiplying the two matrices and noticing that the result will be the identity. Because these two matrices are 2 by 2 matrices, the result will be the identity 2 by 2. Obviously, we have two matrices 3 by 3. When we multiply, if they are the one is the inverse of the other, then when we multiply them, the answer will be the identity, the 3 by 3 identity. So it will be easy to check if two matrices as the inverse one of the other. You can multiply D times C just for you to try, and you will notice that the answer will be the same. So anytime that AB is the identity, then BA will be also the identity. See, that will be a property. I know that the multiplication in matrices is not a commutative operation. However, in this case, there will be something that always satisfies. AB equal BA in case that AB equal I. No in other cases. There will be cases when AB is different than BA. But if the AB is the identity, then BA will be also the identity. So if A is the inverse of B, B will be also the inverse of A. So this is a mathematics property of matrices. But not all matrices have an inverse. Let A be a square matrix satisfying that the determinant of A equals 0. If that happens, if the determinant of A is 0, then the inverse does not exist. So that will be happening that in the case of the real number 0 that doesn't have an inverse, then there will be many matrices. Anytime that the matrix, the determinant is 0, the inverse does not exist. And we call these matrices a singular matrix. We say that A is a singular matrix, it doesn't have an inverse. Or, in another word, if the determinant of the matrix is 0. But how we compute this matrix? How we compute the inverse of the matrix? Because so far what I have told you is how to check if the two matrices are the inverse of the other. But what will be the way to work if we want to find this matrix? And that's what we are going to explain now, how to find the inverse of a matrix. We can compute the inverse of a matrix if we observe the following. Assume that E1, E2 until the last one, Ek, be elementary matrices of the same size of A. And that satisfies that if you multiply E1 times E2 times all of them until the last one, Ek, multiply by A, you get the identity. If that happens, if you multiply all these matrices and you get the identity, obviously, if you multiply E1, E2, Ek, until Ek, you are going to find a matrix. So this matrix will be the inverse of A because we are obtaining the identity. Then we are going to say that A is an invertible matrix, and the inverse of A is given by this product. E1, E2 until Ek. So we can say this. And obviously, we are going to have a formula to compute A minus 1 if we found these elementary matrices. And when you have a matrix like this, it's the same of the same matrix multiplied by the identity. Because when we multiply a matrix by the identity, I obtain the same matrix. So these two statements here are equivalent, this or this. But what I'm telling you with the second one, if the inverse of the matrix A is equal to the product of the same elementary matrices that I use to obtain the identity from A. But why it is important to write it in this way? Because we need to remember that remark that each elementary matrix is equivalent to an elementary row operation. So multiplying all these matrices by I means the same that making row operations in the identity. And what row operations are you going to make in the identity? The same row operation that I make to convert A in I. So that gives me a way to obtain the inverse of a matrix. So from this, we can infer two important affirmations. First, to be invertible a matrix, there must exist elementary row operations. Here I say elementary matrix, but I know that elementary matrix is the same of elementary row operation. They are equivalent to row operation that applied to A produce the identity matrix. So to be invertible a matrix, we need to have elementary row operation that transform the matrix in the identity. And second, if we apply the same operation to the identity, look at here, if we apply the same operations that I made to transform A in the identity, if I apply these operations to the identity, I'm going to find the inverse of A. So this statement is giving me a way to find the inverse of a matrix. And for doing that, we're going to use something that is called the augmented matrix for computing the inverse. For whatever n by n matrix, we can construct an n by 2n matrix. So a matrix that have the double number of columns by appending the n by n identity matrix to the matrix A. I'm going to tell you what is the reason, what is good to do that. The augmented matrix for computing the inverse will be always in this way. So we are going to put the matrix A and then we are going to append the identity of the same side at the other side. And obviously now we are going to have the double number of columns. For example, if we have this matrix and I want to construct the augmented matrix for computing the inverse, what I'm going to do is put beside A the identity of size 4 by 4. So the augmented matrix will be this same matrix that we have, and I'm going to put the identity of the same side at the other side. Obviously, at the end we're going to have a matrix that have the same number of rows but the double number of columns. So I'm going to make row operations in the augmented matrix, and by doing that I will be sure that I will be making the same operations in the matrix A and in the identity. That will give me a way to compute the inverse, because if I transform this in the identity, then this one will be transformed in the inverse. And that is what this statement is telling me. If I made the same operations in A that in the identity, A will be transformed in the identity and the identity will be transformed in the inverse of the matrix. Let's summarize the step that we need to make to get the inverse of a matrix A. First, construct the augmented matrix AI. So attach I on the right side of A. Doing that, you ensure that you're making the operations in A, you are also making the same operations in the identity. And what type of operations you are going to make? Operations that transform this augmented matrix in this IB. So you are thinking in transforming this A in the identity and making the same operations at the other side. You are transforming this matrix I in another matrix. This matrix B will be the inverse of A. So the inverse of A will be the one that appears attached to the identity at the end of the process. And we write the inverse of A equal B. For example, you can have this matrix and you can find the inverse using this algorithm. The first thing, remember, make the augmented matrix. So let's do it here below. So I type the matrix A, and on the right side I attach the identity. This line is good for separating the two matrices in such a way that at the end you are going to see the inverse separated of the identity at the end. So let's close the bracket and let's make operations trying to transform. I'm thinking transforming the first matrix in the identity, making row operations in such a way that this matrix transform in the identity. So the first thing that I notice is that the identity have a number 1 here. So it will be a good idea in this case divided by 2, the first row. So make an operation that transform this number that appears in the A sub 1, 1, transform this in a number 1, because you are trying to transform this in the identity. Observe that you want to have the identity on the left side of this. So let's see, let's divide it by 2 this. So the operation that I'm going to do is 1/2 of R1, and that will be replacing the previous R1. So that's what we are going to do. And this operation needs to be done in the whole augmented matrix. So it means that you are going to make the same operations in the matrix A and in the identity. Let's do it. So these 2 will be, when you multiply by 1/2, this will be 1. This 4 will be 2. Dividing by 2 is the same of multiplying by 1/2. So this will be 1. This 4, there will be a 2. This 6 will be 3. This 0 remains 0. So this will be row equivalent to this matrix. So it will be here 1, 2, 3 in the first row, and the other part of the matrix remains the same. Obviously, we need to make the same operation at the other side. No movement in the other 3 rows. Yeah, so the other 3 rows continue being the same, but I was dividing the first row by 2. So this number here will be 1/2 or 0.5 if you want. I prefer, if I'm working by hand, I prefer to use fractions because the answer will be at the end exact answers. So let's see. So there will be 1/2 here, 0, 0, 0, and then, so when you divide 0 by 2 is 0. All of this 0 divided by 2 will be 0, and close the bracket. So that will be the new matrix. This matrix is different than the previous one. It's row equivalent, but now it's closer to the identity. As you can see, this is more similar to the identity. I recommend you to focus in the first column first. Remember, the first column of the identity will have a 1 at the top and 0 below it. So these 2 need to be a 0. Fortunately, these are already 0, but these 2 cannot be a 2. Need to be a 0 if we want to have the identity on the left side. So let's do this operation. Now, there is no multiplication, there is no division that you can do to transform a number in 0. What you can do is add a product of the first, of the one that already have a 1. So for example, if you multiply this by -2 and add it to the last row, you're going to have a 0 here. So let's do it. Multiply the first row by -2 and add it to the last row. So it will be R4, the row that I'm going to change, minus 2 times R1. So I'm multiplying this by minus 2 and adding this. Always that's gonna work. If you have a number 1 already in the column, one way to transform a number in 0 will be adding to the row that you want to transform, the row, when you see the number 1, multiply by the negative of the number, by the opposite of the number that you want to transform in 0. This was a 2, so you multiply by a minus 2. So R4 minus 2R1, so it will be here 2 minus 2, it will be 0 here. Here will be, when you multiply this by minus 2, there will be a 4. So it will be 5 minus 4, it will be 1 here. 0 minus 0, here will be 0 minus 3, so minus 6. 3 times 2 is 6. So it will be 0 minus 6, it will be negative 6 here. This here, when you are making the operation on the other side, will be 0 minus 2 times 1 half is 1. So it will be 0 minus 1, it will be minus 1. So let's see how is everything transforming. So it will be the first row doesn't change. The row that you are going to change is R4. And then will be again 2 minus 2 is 0. 5 minus 4 is 1. So 5, 0, 1, 0. And the last one will be 0 minus 6. It will be minus 6. Then at the other side, you are going to do the same. 0, so remember, you are going to make the same operations in the identity. 0 minus 1, it will be minus 1. So the first row doesn't change, but the last one will have here a minus 1. Okay? So it will be minus 1. Here it will be 0 minus 0 is 0. 0 minus 0, when you multiply 0 by 0, 0 by minus 2 is 0. So 0 minus 0 is 0. 1 minus 0 is 1. So this will be the number here. And this will be the new. So we are transforming the first matrix in the identity, and by doing that, we are transforming the identity in another matrix. And I know at the end here, we're going to have B. If this is invertible, if actually we can transform this A in the identity. And now, focus in the second column. The second column should have a 1 here. So one idea will be just making row swap between these two rows, and you're going to put a 1 here. Interchange R2 and R4. So, change in the first and the third row, but now here will appear 0, 1, 0 minus 6, that was before in the fourth row, now will be in the second. And the second will be in the fourth. So here we have the 0, 1, 0 minus 6, and here we have 0, 0, 3, 1. And you are going to do the same at the other side. This one will be 1 half, 0, 0 doesn't change, so the first row and the third row doesn't change, but now you interchange these two, the second and the fourth. So it will be minus 1, 0, 0, 0, 1 here, and here will be 0, 1, 0, 0. And that changes the matrix that we have here. Now it's more similar to the identity. You see now they have a 1 here. The only that is missing is to put a 0 in the second column, to put a 0 here. It will be easy to transform this in 0. This minus 2 times the second row will put a 0 here. So the operation I'm going to do will be R1, so the row I'm going to change, minus 2 times R2. And obviously when I do this, it will be row equivalent to, it will be 1, here will be 0, here will be 0 minus 0, 0, and here will be 3 plus 12. When I multiply this by minus 2, was plus 12. And look at that, this one doesn't change because you have put a 0 first beside. So this 0 is not going to change this number 1. So for that reason, it's a good idea to be working in order from the left to the right. You are filling with 0, and the zeros are not damaging the numbers, the ones that we already have. The matrix at the left side have changed in this way. Now at the other side, again, the 3 last row doesn't change, but the first one, again, the first one minus 2 times the second. So it will 1/2 plus 2. So it will be 1/2 plus 2. So it will be 5/2. So it will be 0 plus 0, 0, 0 plus 0, 0, 0, minus 2. It will be minus 2. So I'll close the bracket. So now you finish with the second column. Go to the third column. Put a 1 here and 0 in the others. And I'm really happy that the 1 is already there. So I don't need to do anything. If there was a 7 here, so I divide by 7. Since anyway will be easy making operations in a row, transforming a row, a number in 1, just dividing by the same number. In this case, it's already 1, so I don't need to do anything. So by interchanging rows or by making a division or a multiplication by the inverse of the number. Okay, anyway, the 1 is already here and the others are 0. Very good, I'm happy about this, but this 3 cannot be 3. The fourth row minus 3 times the third row. So the first row minus 3 times the one that have the number 1. So it will be R4 minus 3R3. That will be changing the row number 4. And we're going to have a row equivalent matrix. Obviously, there are some rows that doesn't change. The row that we are changing is R4. And R4 will be R4 minus 3 times this. It will be 0 minus 0, 0, 0 minus 0, 0. But 3 minus 3, when you multiply this by 3, will be minus 3, 3 minus 3, 0. And here will be 1 minus 0, it will be 1. So it will be 0, 0, 1. And then at the other side, doesn't change the first rows, but the last one will be 0 minus 0 is 0, 1 minus 0 is 1. Then here will be 0 minus 3, it will be minus 3. So it will be 0, 1, minus 3, and 0, the last one. And now we are closer to the identity. But the only that is missing is put a 0 here in the fourth column. Now we are going to the fourth column. If this is not number 1, if this is number 20, one way to put it as number 1 is divide by 20. This row. In this case, it's already number 1, so that I'm just focusing in this negative 6 and this 15. Put this at 0. How can I put this negative 6 at 0? This row plus 6 times the fourth row. This 15, how can I put a 0 here? The first row minus 15 times the fourth row. So we can actually make the 2 operations in just one. So I'm going to, the row 1, I'm going to make a subtraction of 15 times R4. And for the row 2, I'm going to make row 2 plus 6 times R4. And that will be changing these rows. And let's do it immediately. So there will be equivalent. At the beginning, we have then 1, 0, 0, and 0 here when I make this operation. So the other rows doesn't change, but here will be 1, 0, 0, 0. The other will be 0, 1, 0, 0 when you make this operation. R4 plus 6, R4. So transform this in 0. What will be the transformation at the other side? We know the last 2 rows doesn't change, but the others, so it will be here 5/2 minus 15 times this number, but this is 5/2, doesn't change. This 0 minus 15 1, so it will be minus 15 here. This 0 minus, here when I multiply by minus 15 will be plus 45. So this number will be 0 plus 45. And this will be minus 2. And this minus 15 times 0 is 0, so it will be minus 2, doesn't change. So what the changes are 5/2 minus 15, 45, and negative 2. And this one will be minus 1 plus 0 is minus 1. 0 plus 6, because I'm multiplying for changing R2, I'm multiplying by 6 this. 0 plus 6, it will be 6. So this 0 will be transformed in 6. 6 multiplied by minus 3 minus 18, 0 minus 18. It will be minus 18. And this will be 1 minus 0. Or 1 plus 0 is 1. So the numbers here will be minus 1, 6, minus 18, and 1. Close the bracket. We have the identity here. So this matrix here will be the inverse of A. So then the inverse of A is this matrix. And obviously I understand that this is a long work. Anyway, it's good to know what is the algorithm, but obviously that can be done using a software. We call this the echelon form of the matrix. If we have a matrix like this, the augmented matrix, and we transform the matrix in such a way that the first element of the row is number 1, then we have found the echelon form of the matrix. I will be focusing now in speaking about this echelon form of the matrix. Let's review the step for effective row operations in the augmented matrix of A for obtaining the inverse of A. The method is called the Gauss-Jordan method. For doing this method, the first step is to make A sub 1, 1 equal 1, either by interchanging rows or by multiplying the first row by a suitable constant. If the initial A sub 1, 1 is different than 0, for example, is a number A sub 1, 1 equal R, and this R is different than 0, you can multiply the row by 1 over R. That always works. In our example, remember, we have the augmented matrix like this, and we multiply the first row by 1 over 2. That will always work because the first A sub 1, 1 was 2. I multiply by 1 over 2, and that for sure makes this number 2 equal 1. So the result was this. This is the first step. Make this number a 1. After that, as step number 2, perform row operations in the resulting matrix to make 0 the other entries of column 1. So try to make 0 the others. In our example, they were already 0 except the last one. So I will make an operation to make this 0. And this always work. Like if you notice that this number is R, then will be the row in which you want to put the 0 minus the row that have the number 1, the first row in this case, multiply by this number. So minus 2 times in this case, minus 2 times the first row. If this is 3, minus 3 times the first row. If this is minus 4, then it will be plus 4 times R1. If there is a 1 here, there is always a way to put a 0 in the other entries of the same column. So in this case, what I did was R4 minus 2 times R1, and that makes 0 this. Obviously, by doing this operation, also change things in the other side of the matrix, of the augmented matrix. So these are the first steps. Making 1 first, and then making 0 the rest numbers of the column. Okay, as a step number 3, you are going to repeat these 2 first steps, but now trying to put the number 1 in A sub 2. And after you put number 1 in A sub 2 by interchanging rows or by multiplying by a number, then put 0 in the other entries. In this case, what I need to do is just making a row interchange. After I made the row interchange, I put a number 1 here. And then do the same in the others column. So as a step 4 is again repeating step 1 and 2 in order for each of the other columns. And you stop when you obtain a reduced row echelon form of the augmented matrix. So after each of the elements in each of the row is number 1. If this RREF is of this form, have the identity on the left side and another matrix in the left side, then you stop and you say that the inverse of the initial matrix is the one that appears on the right side. Okay, so that's what I did in a previous slide. So we were performing the steps 1 and 2, so making 1 and then 0 in each of the column, and then try to put the number 1 in the next one, but it was already there, and put the 0 in the others entries of the same column. And at the end, when you get, if you get a different number, for example different than 1 in the H.44, it will be easy just multiplying by 1 over that number. After you get a 1 here, it will be easy to transform in 0 the other elements in the same column. And at the end we get a IB form. So the identity on the left side and the matrix that we obtain on the right side is the inverse of the initial matrix. This is a reduced row echelon form, RREF, or the augmented matrix. And you should stop at that point. The inverse of A will be then